Welcome back to the Deep Dive, where we take the sources you provide us, the articles, the research, the deep technical reports, and give you the distilled insight.
And today, we are really getting into the weeds.
We are. We're not just looking at a chip. We are dissecting a custom-built supercomputer that was, basically engineered to defy the limits of physics and change the course of AI.
We've been handed a deep dive into Google's Tensor processing units, specifically the second and third generations TPUv2 and TPUv3.
Right.
And these were born out of a stark necessity. So one of those great inflection points in, modern computing history.
And that necessity is our hook. The AI race and the hardware ceiling, the foundational wisdom of deep neural networks. Generally, bigger models and more data lead to bigger, more impressive breakthroughs.
Absolutely. But scaling that breakthrough requires just utterly astronomical amounts of computation.
Just how bad was it?
Well, the sources detail this terrifying exponential curve. The computation required for the largest training runs grew by a factor of 10.
10 times.
Annually. Yeah. Every single year between 2012 and 2018.
That's just an explosive, unsustainable rate.
Exactly. And no existing hardware could possibly keep pace with that.
Which brings us to the core issue plaguing the entire field, the deceleration problem.
Yeah.
For 50 years, innovation really relied on Moore's law, that predictable doubling of processing power in general-purpose CPUs every 2 years or so.
But the sources confirm that performance improvement in those microprocessors just slowed down dramatically. The general-purpose engines were sputtering out.
So when that engine slows down, you have to pivot.
You have to. Innovation was forced away from those general-purpose CPUs and toward what we call domain-specific architectures, or DSAs.
So if you can't make a chip that does everything twice as fast,
you have to make a chip that does one critical thing 50 times better.
And that one critical thing for Google was solving the training challenge. So we are diving into the Tensor processing unit, the TPU, generations 2 and 3.
And these are not just, plug-in accelerator cards. These were the first production DSA supercomputers. Massive, networked systems designed exclusively for that brutal, demanding task of training deep neural networks.
So our mission today is to unpack the key architectural choices that created this machine.
Exactly.
We want to know how TPUs managed to train these networks up to 50 times faster and offer 5 to 10 times better performance per watt than traditional supercomputers.
It's a huge claim.
It is. And let's set the stage really quickly. We know about the first TPU, TPUv1. That chip solved the inference problem.
Right, the quick, efficient serving of the finished model out in the real world.
And it was a huge win, a 50 times improvement in performance per watt for those inference workloads.
Yeah, but inference is, it's the easy part. The existential question that Google's engineers were facing was, can we take that initial success and scale it up?
To get the same kind of breakthrough.
Exactly. A 50 times leap for the much, much harder problem of training. So to really appreciate the design of TPUv2 and v3, we first have to understand why training is just fundamentally so much more difficult than inference.
Right. Why it requires this custom hardware. Okay, let's unpack this. We'll start with the basics. DNN fundamentals. We've got weights and layers. A network transforms an input to an output through all these layers, and the knowledge is stored in millions, now billions, of these calculated weights or parameters.
Precisely. And training is that intensive, sometimes months-long process of finding the best values for all those weights.
It starts with random weights.
Random weights. And you use a huge data set of known good pairs. You supervised learning. And this whole process relies on these iterative steps called stochastic gradient descent, or SGD.
And that SGD loop, that's where all the complexity piles up. Can you walk us through the 4 steps and really highlight where the true computational bottleneck is?
Sure. The loop starts with forward propagation. The input data runs through the model to produce a prediction. As you said, this is basically identical to inference.
Simple enough.
Second step, loss calculation. The system measures the error, how far off the model's prediction was from the actual correct result.
So far, so good. This all feels like something a general-purpose chip could handle. Then the complexity just spikes.
It does. With step 3, back propagation.
And this is the computational killer.
This is it. The model runs mathematically in reverse, layer by layer, and it calculates the gradient, the error value, for every single weight and every single connection and every layer.
So it requires calculating derivatives for every single computation that happened on the way forward.
Every single one.
Wait, let me just make sure I understand the burden here. Backpropagation isn't just reversing the math. It's asking, if I tweak this one specific weight just a tiny bit, how much would the overall error change?
That is exactly what it's asking. And because you're calculating a derivative for every step, the workload is just massive. It often involves these complex matrix multiplications, but with transposed weight matrices.
Okay, and that's harder.
Much harder. Then finally, the fourth step is the weight update. The system adjusts all the weights based on those gradients you just calculated, scaled down by a tiny value called the learning rate.
So we have this intense cyclical process that has to be repeated millions and millions of times. Why can't you just cluster more CPUs or GPUs together to solve this? What are the key architectural differences between training and inference that just demanded a whole new supercomputer?
Okay, there are 4 critical points. Let's start with the biggest one, harder parallelization.
Right.
Inference scales beautifully. Each calculation is independent. You serve 1,000 users, and those 1,000 calculations don't need to talk to each other.
But training is a group project. It demands coordination for collective learning.
That's the perfect way to put it. A training run might iterate over billions of examples spread across thousands of chips, but it has to produce a single, coherent, consistent set of weights.
So all 1,024 of those chips have to agree.
They have to perfectly reconcile their individual updates at the end of every single step. And that coordination is incredibly susceptible to network latency.
Yeah.
The slowest chip slows down the entire system.
That is a massive synchronization challenge. Okay, so what's difference number 2?
Number 2 is just more computation. Beyond the derivatives and backpropagation, the memory access pattern is way more complex.
Oh, so?
Training requires constantly moving and operating on those transposed weight matrices I mentioned.
Right.
And that's just a more complex and memory-intensive operation compared to the simple matrix multiplication you use in the forward pass.
Yeah.
The total amount of computation is just vastly higher.
And the memory requirements are just staggering.
Number 3, vastly more memory. The sources say that the temporary storage needed for training can be 10 times the storage needed just for the weights themselves. It's a huge multiplier.
Why? Why this massive disparity?
It's all because of backpropagation. To correctly calculate the error contribution, the gradient for a weight in an early layer, the system needs the intermediate activation values that were generated during the forward pass.
So it has to remember what it did.
It has to remember everything. These intermediate values have to be temporarily stored or checkpointed as the data flows forward so they can be accessed when the calculation runs backward.
And for a big model.
For a large model with, say, 100 billion parameters, the memory required to store those parameters and all the associated temporary activations is just enormous. Inference just needs a small working set, but training needs to hold on to everything.
Wow, a 10 times multiplier on memory. That means memory bandwidth and sheer capacity become the main bottlenecks, not just how fast you can do the math.
Precisely. And that leads to the final point, number 4, data width. We love the speed of 8-bit integers, INT8, for fast inference on TPUv1.
But training forces them back to wider data requirements. Why did those tiny 8-bit numbers fail for training?
Training requires higher precision. Traditionally, that meant 32-bit floating point, or FP32. And this is crucial for what's called numerical stability.
Okay.
Stochastic gradient descent involves adding up thousands, sometimes millions, of extremely small weight updates. If you use a format with a narrow range or low precision, those tiny adjustments can just get rounded away.
They just disappear.
They vanish into the noise floor of the chip's arithmetic, and then the model just stops learning. It fails to converge.
So let me get this straight. Training is an architectural nightmare because it requires perfect coordination across thousands of chips, 10 times more temporary memory, and high numerical precision to avoid losing these tiny critical updates.
That's the list.
This basically forced Google to just throw out the entire rulebook.
They absolutely did. They couldn't just build a better chip. They had to build a better system from the ground up to solve all 4 of those problems at the same time.
Okay, so given that formidable list of challenges, let's look at the solutions. We'll start with the DSA philosophy and the course structure. What was the fundamental design compromise they had to make to get these radical gains?
Well, the primary goal was just pure, uncompromising efficiency on DNN workloads. And to get that, they rejected all the general-purpose features that consume silicon area and power, but offer, no benefit for DNNs.
So they intentionally threw out things like large caches, complex branch prediction units, and out-of-order execution.
All of it gone.
That's a radical move. I mean, a CPU architect would call that heresy. Branch predictors and caches are crucial for making normal software run fast.
Of course. But the advantage of tossing them is a massive gain in power and area. The sources highlight that DNNs have these highly predictable sequential data flows.
You know exactly what's coming next.
You know exactly what instruction comes next, and you know exactly what data you'll need. So by eliminating all that complex circuitry for speculation and cache management, they gained back a huge amount of silicon area and saved a ton of power.
Area they could then dedicate entirely to the core computing element.
Exactly.
So they traded that general flexibility for just hyper-optimized efficiency. And instead of dozens of small, complex CPU cores, the TPU chip focused on one or two large cores, the Tensor cores.
Correct. TPUv2 and V3 used 2 Tensor cores per chip. And the decision to stop at 2 brawny cores instead of filling the chip with like 32 wimpy ones, that was also driven by the compiler.
Oh.
It's just far simpler for a compiler to efficiently schedule work and manage memory for 2 big predictable cores than to manage the complexity and latency of coordinating dozens of smaller ones.
Let's zoom in on the heart of the machine then. The matrix multiply unit, or MXU, and the systolic arrays. This is the innovation that makes the TPU a tensor processing unit.
It absolutely is. The MXU is where the vast majority of the computational heavy lifting happens. It's essentially a giant fixed function calculator built specifically for matrix multiplication.
And it's huge, a 128 by 128 grid of multipliers.
Right. And it uses a systolic array. That's a word that sounds dense, but the analogy really makes it click.
Can you re-explain that for us?
Sure. Think of it like a computational water fountain. Or even better, a digital marching band doing a really complicated drill. Instead of pulling data into a single central register to do the math, the traditional CPU method, the data is choreographed.
It's in motion.
Exactly. Input matrices flow rhythmically from different directions across this array of multipliers. The calculation happens in transit, right where the data streams intersect at each cell.
So the data keeps moving, and the results just sort of accumulate as it passes through the system.
Exactly. And that rhythmic flow, that localized processing, it drastically reduces the need to constantly write intermediate results out to registers or memory, which is a huge waste of energy. It maximizes data reuse on the fly. It keeps the compute units completely saturated with work.
You know, I found the decision on the MXU sizing really fascinating. TPUv3 doubled the number of MXUs to 4 128 by 128 arrays per chip. If larger is better, why not just make one huge 256 by 2556 array?
This is a perfect example of domain-specific design being guided by real data. They ran simulations and found that a lot of crucial convolutional models, the backbone of image processing, would dramatically underutilize a single, large 256 by 256 MXU.
They'd be running at what, like 20 or 30% efficiency?
Something like that, 22% to 30% in some cases. The convolutional operations just naturally break down into smaller matrix sizes. The workload wasn't big enough to keep one huge engine busy.
So instead, they doubled the number of smaller engines.
Precisely. By doubling the number of 128 by 128 MXUs to 4, they boosted utilization up to, 37%, 48% on those same models. The gain in efficiency came from matching the physical hardware to the statistical shape of the most common operations.
That is the difference between theoretical peak performance and what you actually get in the real world.
Yes.
Now, all that raw power is useless if the chips can't talk to each other fast enough. Which brings us to the interconnect superhighway, the ICI and the 2D torus. This is what solves that synchronization nightmare of training.
This is maybe the most critical difference between a TPU supercomputer and a conventional cluster. The TPU architecture uses a specialized 2D torus topology.
Okay, what does that look like?
Imagine a massive grid of chips, where every chip is connected directly to its north, south, east, and west neighbors. And then the rows and columns wrap around to form a loop, like a donut.
A torus. And the key here is that the switch isn't some external box.
No, it's baked right into the silicon.
Yeah.
The network switch is distributed into each chip itself. And this allows for 4 custom Inter-Core Interconnect, or ICI, links per chip, screaming along at up to 656 gigabits per second per direction in TPUv3.
That sounds incredibly fast, but what's the practical advantage over, say, a traditional InfiniBand cluster?
Oh, the physical advantage is immense. The network is completely dedicated, and the distributed switching means you eliminate the bottleneck of a big, centralized switch fabric.
Right.
A 256-chip TPUv2 supercomputer delivers 15.9 terabits per second of bisection bandwidth. That is 2.5 times the bandwidth of a standard cluster using InfiniBand, which might top out at 6.4 terabits per second.
And the sources stress that this fast ICI network, with its predictable low latencies, had a huge algorithmic impact. This is where the co-design really comes to life.
Indeed. Because the network was so fast and its tail latencies were so tightly controlled, the architects could abandon the traditional asynchronous approach to training.
They could mandate synchronous parallel training.
Yes.
Okay, wait, let me make sure I understand the old problem first. What was the parameter server bottleneck in asynchronous training?
In asynchronous SGD, different chips or workers would calculate their gradients and then send them off to a set of centralized parameter servers. The workers didn't wait for each other.
Okay.
The servers would aggregate all these updates and then send back the new set of weights. The problem was those servers were a massive bottleneck. And because it was asynchronous, the workers were often training on slightly stale versions of the weights.
Which would hurt the model's performance.
Right. Reduced efficiency and stability.
And the fast ICI network let them do synchronous training instead. Everyone waits for everyone else, updates are guaranteed to be fresh, and you just get rid of that central server bottleneck entirely.
Exactly. All 1,024 chips start, process, and reconcile weights at the exact same time. This unlocked that near-perfect scaling, which was just impossible with the old topologies.
So better hardware didn't just speed up the process, it enabled a completely superior algorithmic strategy. The architecture solved the algorithm's biggest scaling problem.
That is the definition of co-design. Which brings us to the last piece of the puzzle. The data precision breakthrough, Brainful at 16 or BF16.
Right. We established that training needs higher precision than inference, but full 32-bit floating point is slow and expensive. Why couldn't they just use the standard 16-bit float, FP16, which Volta GPUs were adopting?
The problem is in FP16's structure, it uses a very small 5-bit exponent.
And the exponent controls the range of numbers you can represent.
Exactly. Because that range is so narrow, when you're calculating the gradients in SGD, those tiny weight updates often fall outside the available range. They underflow. They just become zero.
And your training fails.
It just stops working. Standard FP16 sacrifices way too much range for precision.
So the system needed the wide range of FP32, but the small size of FP16. That sounds like a contradiction.
That's where BF16 comes in. They split the difference, but they prioritized the component that mattered for DNNs, the range.
So what did they do?
The new format keeps the generous 8-bit exponent identical to the massive range of FT32, but it drastically reduces the mantissa, the part that dictates precision, from 23 bits down to just 7.
So you sacrifice some fine-grained detail, but you ensure that even the tiniest weight adjustments remain visible within the numerical system.
The compromise was absolutely perfect for deep neural networks, and the benefits are crucial. In hardware, a BF16 multiplier is about half the size and uses half the energy of an FP16 multiplier.
And there's a massive software benefit too, right?
A huge one. Simplicity for the programmer. Using standard FP16 requires these complex manual software workarounds called loss scaling. You have to constantly shift numerical values up and down to keep them from slipping out of that narrow exponent range.
It sounds like a nightmare to debug.
It is. With BF16's wide range, that entire layer of software complexity is just unnecessary. It reduces hardware cost and energy while simultaneously simplifying the software stack. That's why the sources predict BF16 is going to become the industry standard for these kinds of chips.
So we have this beautifully optimized, highly specific hardware, but custom hardware is useless without custom software. Let's look at the TPU software stack. How does XLA accelerated linear algebra bridge that gap between a high-level Python framework and this exotic silicon?
Well, the machine learning engineers, they still use TensorFlow, which is a Python-based framework, but XLA is the specialized compiler that does all the machine-dependent mapping. It's really the central nervous system that makes the hardware run efficiently.
What's the advantage of working with a Python ML framework for the compiler compared to, say, traditional C++ way?
The sources note that ML frameworks offer higher expressiveness and, crucially, much better optimization information.
How so?
When you write a program in TensorFlow, you're explicitly defining a computation graph using these multidimensional arrays, or tensors. The data access patterns are open, they're analyzable, they're predictable.
So the compiler can see everything.
It knows exactly what data needs to go where and when. It can analyze memory aliasing behavior perfectly, something traditional C++ compilers really struggle with.
So that high-level language gives the compiler maximum visibility into the underlying math, which is exactly what a specialized supercomputer needs.
Precisely.
Let's dive into XLA's compiler magic then. Since TPUs intentionally threw out caches, XLA has to do jobs that hardware usually handles automatically.
That's right, because the TPUs rely on software-controlled scratchpad memory. This local high-speed RAM that's managed explicitly by the program XLA takes on this gargantuan task of memory management and scheduling.
So what is it actually doing?
It's mapping all the memory transfers, all the data movement, all the parallelism across hundreds of chips, thousands of MXU multipliers, and the 2 tensor cores. It's like a super optimized orchestra conductor controlling every single movement across the entire data center.
And the key optimization that delivers these huge speedups is operator fusion. Can you detail exactly how that reduces the memory bottleneck?
Sure. Operator fusion is the process of combining multiple sequential operations into a single kernel, and that reduces memory traffic. So imagine you have two steps. First, a matrix multiplication, and second, an activation function, like a ReLU.
Traditionally, those are two separate instructions.
Yes. The system would do the matrix multiplication, write the huge intermediate result array back out to the high bandwidth external memory, and then read that same array back into the chip to perform the activation function.
And that write-read cycle is slow and expensive.
Very slow and energy expensive. XLA analyzes the graph, fuses those two operations, and schedules them together.
So it skips the round trip to memory.
It skips it entirely. The matrix multiplication result is kept right there in the on-chip registers and fed directly to the activation function unit before it ever touches external memory.
And the speed up from that.
The sources show this one optimization delivered massive speedups, anywhere from 1.8x to a stunning 6.3x on various models. That's pure free performance from a software trick.
That is architectural efficiency unlocked entirely by software. And the concept of composability is also pretty remarkable. XLA only needed 96 target operations, or ops, to handle all the complexity of TensorFlow.
Yeah, it vastly simplifies the engineering effort. Instead of writing custom assembly for every little variation of a TensorFlow function, XLA can synthesize thousands of high-level ops from that tiny set of 96 primitives.
Which means it's much more adaptable.
It can adapt really quickly when a new model or a new technique is introduced without needing a complete library overhaul.
And the proof is in the pudding, right? The source material noted that between MLPerf versions 0.5 and 0.6, the TPU median speedup was 2.1x in just 6 months.
Right, compared to 1.3x for GPUs. It shows that the XLA stack was still, relatively immature, but was improving at a really rapid pace. Even with fixed hardware, the co-design software system has this huge capacity for optimization.
Let's get to the head-to-head comparison that everyone cares about. NVIDIA's Volta architecture was the reigning champion in the AI world at the time. What's the fundamental architectural philosophy contrast between the TPU and the GPU?
The core philosophical difference is really deterministic control versus latency tolerance.
Okay, unpack that.
The TPU is a deterministic, compiler-driven, in-order machine. It assumes the workload is predictable, and it demands high batch sizes to amortize its memory costs. XLA dictates every single move.
And the GPU is a master of hiding complexity.
Exactly. The GPU, specifically Volta, is a latency-tolerant many-core machine. It had 80 cores. It anticipates memory latency and hides it with just sheer brute force multi-threading.
How does it do that?
It switches rapidly between thousands of threads, supported by these massive register files, 20 megabytes of them. So if one thread is waiting for data, others can immediately pick up the slack and do work.
So the TPU says, we will engineer the system and the workload to ensure there's low latency, while the GPU says, we accept high latency and we'll just hide it with parallel redundancy.
Precisely. And the source analysis concludes that the GPU approach, while it's flexible for general computing, it incurs this high overhead in performance, silicon area, and energy precisely because of that heavy multi-threading complexity.
Which is unnecessary for DNNs.
Right. Since DNN memory access is sequential and you can prefetch it, all that complex latency hiding circuitry is kind of redundant for the core task. The TPU's simple systolic organization captures the data reuse much more efficiently.
That's a huge architectural split. Now let's talk precision in processing. We already detailed why BF16 is so good for training. How did Volta's use of FP16 impact their design?
Well, Volta was highly innovative in adopting reduced precision systolic arrays, but they chose the standard FP16 format.
And as we established, that requires those complex software workarounds like loss scaling to work reliably.
And the engineering cost of that choice is twofold. First, you need that complex, failure-prone software. And second, the sources suggest that the FP16 multiplier actually requires extra die area and energy compared to the streamlined BF16 multiplier.
Even though they're both 16-bit format.
Even though they're both 16-bit. So the TPU enjoyed both a hardware advantage, a smaller, lower energy multiplier, and a massive software simplicity advantage because it didn't need loss scaling.
That's a huge competitive edge. And this efficiency, it has to translate directly into cost.
It does, and that's crucial for organizations running these models constantly. Let's look at the cost and efficiency comparison from the paper. We have 3 robust measures, even accounting for differences in semiconductor tech.
Let's start with capital costs, the cost to build the chip.
Okay, adjusted die size. The Volta GPU die is more than twice the size of the TPU.
And a bigger die is a more expensive die.
Much more expensive. The capital cost of a chip is highly correlated with its size. A smaller die means you get more chips per wafer. So the inherent manufacturing cost of a TPU is significantly lower.
Okay, what about operating costs, like power?
The power, or TDP, difference is clear. For a 16-chip system, the Volta needed 12 kilowatts. The TPUv2, only 7.7 kilowatts.
Wow.
The GPU power consumption was consistently 1.3 to 1.6 times higher. When you run thousands of these chips, 247, that difference is enormous.
Electricity and cooling, yeah. And finally, the direct cost to the end user, cloud rental price.
The cloud price analysis shows that the hourly rental price on Google Cloud Engine was 1.6 to 2.9 times higher for the comparable GPU system than for the TPUs.
That's fascinating. So the takeaway isn't just that the TPU is faster, it's that it is consistently and significantly cheaper, half to 3/4 the cost across capital, operating, and rental expenses.
The argument for DSA in this domain becomes almost unassailable. The efficiency savings are transformative. When models require months of continuous training, reducing the cost by 50% or more changes which projects are even economically feasible.
So the TPU is cheaper, it's more efficient, and it's specialized. But does it actually outperform the champion in real-world scenarios? Let's start with chip performance benchmarks.
So when you compare single chip performance using standard industry metrics, like the MLPerf 0.6 benchmarks, the TPUv3 and the Volta GPU performed pretty similarly.
Okay.
Both demonstrated roughly a 1.8x to 1.9x speedup over the previous TPUv2 generation. So chip for chip on synthetic tests, they're competitive.
But the moment we shift to production workloads, the disparity is just shocking.
This is the definitive metric for DSA success. When running Google's 6 largest production applications, the models that underpin search, translation, and other key services, the geometric mean speedup was 1.8x for TPUv3, but only 0.4x for Volta.
Wait, hold on. Volta was slower than the old TPUv2 on the workloads that matter most. If they perform similarly on MLPerf, what caused that catastrophic performance drop for the GPU?
The root cause again comes back to data precision and software complexity. The engineers running these massive long-term production applications, they avoided the complexity of manually implementing and debugging loss scaling and all the other adjustments needed for FP16 on the GPU.
So what did they do instead?
They just defaulted to the slower but numerically stable 32-bit floating point, FP32.
So the GPU was running arithmetic, that's 8 times slower, while the TPU was just effortlessly running the highly efficient BF16 thanks to its superior range.
Exactly. The TPU's architecture made the efficient path the easy path, which is critical in a production environment where stability is everything.
That really highlights that efficiency isn't just about peak FOPS, it's about how easily the hardware lets engineers safely use high-efficiency arithmetic.
Absolutely. Now let's talk about supercomputer scaling. This is the ultimate test of that ICI network. Did they actually solve the coordination nightmare for 1,000 chips?
That was the promise of synchronous training.
And they delivered. The TPU supercomputers achieved a phenomenal 96% to 99% of perfect linear speedup when scaling up to 1,024 chips on 3 of their major production applications.
That's nearly perfect.
It's unheard of in high-performance computing, where you usually see diminishing returns kick in much faster because of network bottlenecks. This proves the ICI torus and the synchronous training approach were revolutionary successes.
Let's look at the impact with some application examples.
The rise of convolutional neural networks, or CNNs, is a great example. They expanded from just 5% of the total training workload in 2016 to 24% by 2019.
And one of the most famous models using CNNs is
CNN, or AlphaZero, the reinforcement learning algorithm that mastered Go, chess, and shogi, trained entirely on TPUs.
That is the highest profile breakthrough running on this custom efficient hardware.
And another crucial case is the transformer architecture.
The foundation of modern LLMs.
Exactly. This neural architecture, which underpins modern translation and generative AI, it emerged and grew rapidly in popularity, precisely because it's more amenable to parallelization than the older sequential RNNs. The TPU's performance and programmability allowed the transformer to quickly replace the RNN as the dominant model for sequences.
This allows us to make a crucial contrast with traditional supercomputers. Traditional HPC is measured by the LINPACK benchmark, right? Using manufactured synthetic data.
And the comparison is really illuminating. The TPUv3, running AlphaZero, a real-world application on real data, achieved 70% of its theoretical peak performance.
And traditional supercomputers?
Running the synthetic LinPack benchmark, they typically hover around 60% of their peak. So the TPU maintains better utilization on genuinely useful tasks.
And the efficiency difference is staggering. We use the Green 500 list to measure performance per watt. Where would the TPUv3 running AlphaZero rank?
It would rank number 1, and by a massive margin. The TPUv3 achieves 146.3 gigaflops per watt.
And the best traditional supercomputer at the time?
ABCI, which managed 14.4.
That's a 10 times better energy efficiency.
It's 5 to 10 times better while executing a production application. This fundamentally redefines what it means to be an efficient supercomputer. The traditional metrics are measuring speed on a task nobody actually cares about anymore.
Right. And finally, we have to touch on inference on a training chip. If these are so specialized for training, can they still do inference well enough for production?
They do, and they're essential for applications that need frequent retraining on fresh data. The TPUv2 and v3 handle inference using BS16, and the sources show the LSTM0 benchmark ran 5.6x faster on TPUv2 than on TPUv1.
And crucially, the response time, the latency, was lower.
2.8x lower at 44 milliseconds. That improved latency is vital.
Because low latency lets you use larger batches in production for higher throughput, while still meeting those strict real-time response targets you need for services like search or live translation.
It's a win on both the training and the inference fronts.
We've spent this time celebrating the brilliance of the domain-specific architecture. But the inherent risk of a DSA is fragility, right? If a breakthrough algorithm comes along that doesn't fit the MXU or the VPU, doesn't the entire custom design risk becoming obsolete overnight? This brings us to handling algorithmic change and adaptability.
That is the central trade-off of a DSA, and the sources give us a fantastic anecdote. The batch normalization crisis.
Right.
During the TPUv2 design in 2015, batch normalization, or BN, emerged. It was a new technique that stabilized training and reduced the time to train by up to 14 times. It became an instant requirement for modern DNNs.
So a massive, unexpected algorithmic shift right in the middle of their design cycle. How did the architects pivot without scrapping the whole design?
Well, BN required a lot of complex vector arithmetic, including dividing vector additions over the batch, plus this critical inverse square root operation.
So things the chip wasn't designed to do.
The original vector processing unit, the VPU, just wasn't robust enough to handle the sheer volume of vector ops it required. So the quick design fix was twofold. They added a second SIMD dimension to the VPU, making its registers 128 by 8 instead of just 1D 128 wide. And they rushed the inverse square root operation into the chip's transcendental unit.
That is remarkable flexibility for an architecture that intentionally rejected general-purpose components. They managed to adapt the fixed function design to a completely new algorithmic requirement within the design window.
It shows that DSAs don't have to be brittle. They just need to build in strategic flexibility for the known unknowns of AI research.
But even with that success, the architecture still faces current limitations and challenges. Not all DNNs scale perfectly, even on that flawless ICI network.
Now, the weakest link in the chain are models that are heavily dependent on embeddings.
What are those?
These are models like many multi-layer perceptrons or MLPs used in things like ad targeting or search ranking. They rely on these massive lookup tables, link traversal, and variable length data inputs. And all of that results in irregular and highly memory-intensive access patterns.
So the memory accesses aren't sequential and prefetchable anymore.
Exactly. The patterns are irregular. And when the memory access is irregular, the deterministic, compiler-controlled nature of the TPU really starts to struggle.
How badly?
On a 1024-chip system, these MLP models were limited to only 14% and 40% of perfect linear speedup.
So the problem has shifted. They're no longer bottlenecked by the network or by computation.
They're bottlenecked by irregular memory access patterns. This is the new frontier for hardware designers.
And despite these hurdles, the rapid speedup we saw in MLPerf, that 2.1x gain in 6 months, it suggests the software compilation stacks are still maturing at an incredible pace.
It's a field in hypergrowth. Optimization is happening at all levels at the same time. The instruction set, the arithmetic format, the compiler, and the physical interconnect.
So what does all this mean for the future trajectory of AI hardware? What's the core lesson here?
The authors concluded that the ravenous demand for faster DNN training is not going to stop. They expect it to continue growing even faster than general microprocessor improvement ever did.
And the TPU's success validates a singular core principle. The tight, holistic integration of every single component, from the high-level Python framework all the way down to the physical links between the chips, that's the only way to get these exponential gains.
That holistic approach, the tight integration of TensorFlow, the XLA compiler, the TPU architecture, the BF16 arithmetic, and the ICI network, that is the validated path forward for high-performance machine learning. The era of just throwing more general-purpose CPUs at the problem is definitively over. So, to synthesize the major insights from this deep dive, we saw how the sudden stagnation of general-purpose architectures really forced Google into this domain-specific supercomputing world.
Right.
TPUv2 and v3 solved the four massive challenges of training coordination, memory, computation, and precision. And they did it by fundamentally rethinking synchronization with the ICI torus, which enabled synchronous training, and by revolutionizing data precision with BF16.
And crucially, this wasn't just a hardware success.
Not at all. It was a co-design triumph, with the XLA compiler delivering massive gains through software optimizations like operator fusion.
That brings us to our knowledge nugget for you, the learner. Every time you use a massive AI service today, translation, search ranking, image classification, the sheer speed, scale, and most importantly, the cost effectiveness of training that underlying model was determined by a custom architectural decision. Whether it's the efficiency of the systolic array or the numerical stability granted by the BF16 floating point format, specialized hardware is the only reason these models can be trained large enough, fast enough, and cheap enough to be deployed globally to billions of users.
And here is our final provocative thought for you to chew on. The source material mentions that the TPUv3, running real-world applications like AlphaZero, would rank as the most energy-efficient supercomputer in the world.
Right, not using a synthetic benchmark, but running a real complex production-scale task.
Which shifts the goalposts entirely. Does this mean that the traditional metrics for supercomputing efficiency, like the LinPack benchmark used for the top 500 in Green 500 lists, are now fundamentally obsolete in the era of AI?
And if synchronous scaling across thousands of chips is now largely a solved problem, what specific architectural knowledge gap, perhaps those irregular memory access patterns of embedding models, will the next generation of AI hardware need to close?